So a test of independence is where you are testing to see if two variables are influencing one another. So maybe like a crime level. Oops, not crime. Crime. Maybe low, medium, and high is one variable. And then this is something I saw in the past. Weather is another variable. So there's different categories. And the null hypothesis here, the status quo hypothesis would be that crime isn't impacted by weather. They're independent. And you could test that to see whether that's true or not using a chi-square test of independence. And I think what researchers have found is that worse weather is actually influencing there to be more crime, which seems insane, right? You don't think you're going to go rob a car because it's a rainy day and you're feeling blue. Okay, goodness of fit test is a test where you're trying to determine whether a variable is meeting some sort of predetermined pattern or some sort of expected pattern. So the one we often use is we conduct a goodness of fit test to see if our data is normally distributed. If the data was normally distributed, then we'd expect to get certain values, and you can use that for your observed and expected values for the chi-squared test. And then the last one is the test for homogeneity. The test for homogeneity is when you're testing to see whether two variables come from the same distribution or not. Okay, it's a little broad because it doesn't specify what the distribution is, but it's like if you had maybe like the blood pressure of a certain animal in one region in the United States, and you wanted to test to see if the blood pressure was coming from the same distribution in a different part of the United States, you could test with the chi-square test for homogeneity, and that would tell you whether there really is a difference in blood pressure depending on location or not. Okay, but you're probably here for me to just get some examples in, so let's jump into it. University admissions officers trying to determine if men and women have a similar acceptance rates. Okay, so they were testing to see whether the rates of two different groups are the same. So that's where the homo part in homogeneity comes from, being the same. Okay, men and women having similar acceptance rates. We're testing to see whether it's coming from whether those two are coming from the same distribution. Okay, I'm trying to think what I could be confused with. Better not speculate. Okay, so that one, it's two different groups. We're testing to see if they are similar, if their distributions are the same in two different groups. So that's the test for homogeneity. Casino claims a certain game has a third probability of winning $1, third probability of losing $1, third probability of breaking even. So it sounds like we're testing to see whether these games follow a predetermined distribution. Okay, this isn't testing to see if two unknown distributions are the same, like men and women the last time. We didn't have any numbers to exactly compare those two yet. In this case, we have like this predetermined distribution. It's a third, a third, a third. So we're testing to see whether this variable fits this uniform probability, it looks like. So that's a goodness of fit test. Okay, you use the chi-square goodness of fit test if you're just taking like one column of numbers and seeing if it follows a pattern that's already been predetermined. A professor expects that the grades of a recent exam are normally distributed. This is also goodness of fit. Okay, without even reading the rest of the problem, you've got a data set of exam scores. You're comparing it to a predetermined distribution, the normal distribution. If it's not a predetermined, if you don't know what distribution they are, like the men and women from that first example, then that would be a test for homogeneity. Okay, hospitals trying to compare the weights of babies born at night, babies born during the day. Okay, they want to compare the distributions, babies at night, babies at day. I was going to see if it was well, it could have been any three of these until they started talking about whether they wanted to compare the distributions. Babies born at night, babies born at day, two different distributions. We're trying to see if they come from the same distribution, if they're following the same pattern. So it's a test for homogeneity. I don't think we haven't done a test of independence yet, so let's see if it's. A survey company puts out a survey asking people two questions: owns a car or not, supports an environmental bill, contingency table, Company wants to determine if support for the bill depends. Okay, so the question is, if you support the bill, does it affect your car ownership or vice versa? If you own a car, does it affect your support for the bill? So you're testing to see whether these two variables are independent of one another. You're testing to see whether they influence each other. If they were trying to, I mean, no, so you would have to have two different columns of numbers, and you'd have to say that you're testing to see whether supporting the bill people are the same distribution as car ownership people for homogeneity. Okay, but if it's a contingency table, that tends to point you towards a test of independence. It's not always that way, but a contingency table lets you compare those two groups. What were they again? Support the bill. There's yes and there's no, and you're wondering if yes makes it more likely or less likely to own a car. Yes, no for owning a car. Okay, because if you support the bill and you have higher people that own cars and lower people that don't own cars, then those two variables are influencing each other. Maybe owning a car makes you less likely to support the bill. So that's a test of independence. So contingency tables are are how we set up our variables to test to see whether they're independent. Hospital's trying to compare the weights of oh wait, I've already done that one. Okay, I think I've gone through all of them. So a big thing to think about with all these is for each of these test statistics, it's all the same. The chi-squared test statistic is found by summing up, that's what this notation means, add up all the different options for your data set, where you take the observed subtracted by the expected, you square it to make it positive, and then you divide it by the expected value. You do that for the first cell of your contingency table. Take the observed subtracted by what you expect it to be, and that's usually uniform. You expect them all to have the same probability, but that's the same for the goodness of fit test. Same for the test of homogeneity. The expected value is what you expect to have if the null hypothesis is true. Like for the goodness of fit test, like that 1/3 example we had, 1/3 would be all the expected values.